if either one of those two things is odd, then the spin can be non-zero. And if the spin is non-zero, then essentially each nucleus is behaving as a little nuclear magnet. We can perturb that nuclear magnet by putting it in a magnetic field, and that's the basis of the NMR experiment. Okay? Different nuclei have different nuclear spins. You can figure out what the nuclear spin is going to be for a particular isotope, but more likely you're going to refer to a table and just look up the nuclear spin. Okay? Your book has a copy of this table. Every spectroscopy book has a copy of this table. You can look up similar tables online, and you can find that for any given isotope, you can look up the nuclear spin when it's non-zero. So the ones that we're really going to be talking about a lot in this module are proton and carbon, and they're the easiest because they both got spins of 1/2. Okay? If you like this stuff and you go on and take Lisa's module after this, she'll talk more about nuclei with more interesting spins than 1/2, but we're not really going to be talking about them a lot in this module. Keep things simple here. Okay? Anything you want to add?
Oh.
I put you on the spot.
No. There's two things. I don't even know how to calculate this. I just know the ones that are of interest to me. Physics people are really interested in how that calculates. And the most important thing to know about it is that each nucleus has its own magnetogyric or gyromagnetic ratio.
We're going to get to that.
Are you going to get to that?
Yeah.
Okay.
Yeah, well, actually, I'm going to have them calculate the
Okay.
gyro ratio. So, okay, if you take a nuclear magnet, you take any magnet, and you put it in a magnetic field, that nucleus can now orient itself one of 2i plus 1 different ways. Okay? In second year of your undergrad or whenever you started to learn spectroscopy, we sort of gave you this analogy that you can think of a nuclear magnet that has a spin of 1/2 as being either aligned or opposed to the magnetic field. That's a gross oversimplification, but it's a sort of useful oversimplification for now, and so we're just going to stick with it. We might come back and talk more about that, but it's a useful thing to at least kind of keep in your head. Okay. So, if you've got your nuclear magnet and you put it in a magnetic field, which we're going to call B, okay? If we don't turn on the field, those nuclear magnets, no matter which direction they're pointing, are all going to be at the same energy level. As soon as we apply a field, if your nuclear magnet is aligned with the field, it's going to have a lower energy. If it's opposed to the field, it's going to have a higher energy. It stands to reason that the difference in energy between those two states, the splitting, is going to depend on the strength of the magnetic field. It's pretty straightforward. We can look up a formula for the difference in that energy. We could derive it as well, but let's just look it up for the time being. We're going to do lots of calculations as it is. We find that the difference in energy is equal to Planck's constant times this magnetogyric ratio that Chris just mentioned, which is essentially a measure of the strength of the nuclear magnet that you're dealing with, okay? Which we can calculate, or again, we can look up in a table. We'll do a bit of both. Times the strength of the magnetic field divided by 2 pi. Okay, pretty simple formula. Okay, so this is where you get to do your first question. I want you to calculate how big is this delta E difference. And I want you to think about how that delta E difference compares in size to other spectroscopic techniques that you're familiar with, like UV-Vis spectroscopy or infrared spectroscopy. Okay? And I'm going to give you a couple of pieces of information to help you do that calculation. So I'm going to tell you that at a field strength of 7.05 Tesla, the proton nucleus comes into resonance at 300 megahertz, which is why when you walk downstairs into the NMR lab to run a proton NMR, you say you're going to use the 300 NMR, the 300 megahertz NMRs, because that NMR downstairs has a magnet that operates at 7.05 Tesla. Proton comes into resonance at this particular resonant frequency. Carbon on the same spectrometer at 7.05 Tesla comes into resonance at 75.5 megahertz. By the way, that means when you say that you're running your carbon NMR on the 300, it kind of doesn't make any sense, because the carbon's not resonating at 300 megahertz, it's resonating at 75 megahertz. We know what you mean. Okay? There's all the data that you need to to tell me how big delta E is in some kind of real terms. So let's say kilojoules per mole, joules per mole. How big is delta E? And how does that compare to the energy difference in UV or ion? Give you 5 minutes.